Yeah, I'd like to introduce Dom Wirasaet, who's giving today's webinar. Dom's an associate research professor in the Civil and Environmental Engineering Department at University of Notre Dame, and he's kind of an expert on all things numerical. Did his PhD at Notre Dame in 2007, working on adaptive mesh refinement for combustion applications. And since then, he's been with the computational hydraulics lab led by Johannes Westrink at Notre Dame. And he's been developing all kinds of advanced discretizations for coastal storm surge models, like the ADCIRC model that they developed. Today's current work is funded by an ESMD university grant, and I've been lucky enough to be able to collaborate via the ICOM project. And I think it's a really important capability for E3SM's eventual application to coastal inundation problems, and Dom's been a really big part of the success of the project. So go ahead, Dom.
Yeah, thank you very much, Stephen, for a kind introduction, and thanks for the seminar organizer to let me share our work on adding to MPAS-Ocean a subgrid approach that accounts for unresolved topography. I would like to acknowledge a effort from our team at Notre Dame and at DOE, especially Stephen, who does a lot of heavy lifting and kind enough and patient enough to walk me through MPAS code. This slide, I use it to introduce MPAS to people in the computational community, and you guys are all expert in it, so I will skip it. As you guys know, MPAS is the design for global ocean, and currently, according to Mark paper, the MPAS-Ocean component of E3SM resolve the ocean and its coast no finer than 6 kilometers and will not be finer than 2 kilometers in the foreseeable future. This potentially is insufficient to faithfully capture the hydrodynamic exchange between in the coastal zone, right? Which could be really complicated. So this example shows what happened when we approximate the bathymetry of this area in Buttermilk Bay with 8 meters. So you can see that it's actually roughly resolved. But when we approximate it at 200-meter level, you can see that a lot of information are lost, and which means that if we care about the detail inundation or detail physics, using cost resolution would miss the detail, and for the long-term integration, we could miss the high frequency bias. And in my opinion, any method that can increase the accurate predictive capability without increasing the computational time is going to be really helpful. So, and this project, we explore the use of subgrid approach that's akin to volume averaging using the porous media field. And since MPAS code is very complicated, so we focus on our effort in the single layer mode of the MPAS, which was being developed when this project started. The single layer, the governing equation of single layer MPAS-Ocean is shallow water equation with the where the advection term is reformulated into a potential vorticity and the gradient of kinetic energy. Here, the edge is layer thickness, and U is the velocity, depth integrate velocity, and eta is the surface, sea surface height. Um, and in MPAS, as you guys know, it use the polygonal stagger grid polygonal where the layer thickness is placed at the center of the cell, and the normal velocity are placed at the center of cell edge. And this equation here, where my mouse is the semi-discretization, semi-discrete in terms of the above equation, where Hi and He is the layer thickness at the cell center and at the edge, and Cf is the friction coefficient. To include subgrid, is amount to in MPAS-Ocean is simply amount to changing the definition of layer thickness and bottom friction coefficient, as I will show in the next slides. So in MPAS-Ocean, as usual, the layer thickness and surface elevation and bottom depth is defined by this equation. So basically, the layer thickness is a combination of surface elevation and bottom depth, which is 1 YU at per cell. So and the bottom depth can be defined using different methods, and one of them is through the area averaging. So to include subgrid, right, we to correct mass, we change the definition of the layer thickness. So instead of being just a linear combination, so right now, so I form that to the integral over the cell and with a given a given proximity that is spatial varying across the cell. So basically, I need the definition of layer thickness in subgrid approach is defined by this equation, and it practically the as shown in this cartoon picture, it just the average of the wet volume area with a wet average of the wet volume of water ponding the cell. So and the surface a layer thickness along the edge is defined in a similar way. And actually, by doing this, one gain, I would say probably 80 or 90% benefit from subgrid, but sometimes it's not sufficient, and the other correction must be considered. But that one is harder because one need to know one need to have some idea of the subgrid of the flow at the subgrid level. But for one simple assumption, that it's assumed that if a flow at the subgrid level obey the constant friction slope, we can show that the bulk bottom friction can be given by this equation, and it actually can reproduce a channel like flow exactly. So and you might notice that this layer thickness and CF is compute from the known proximity and the given surface elevation. So And because of the only thing we need to know is bathymetry, so we can pre-compute them and store it as a lookup table, and that help reduce the computational cost of the method practically um, with the explicit time stepping. It amount to just very little cost of searching in the lookup table. So this is pretty much what we, in terms of formulation, this is what we need to do in MPAS to add to MPAS, uh, and we also made change to the another important aspect is that we need to make some change to the wetting and drying in MPAS in order to handle the fact that right now um, the thickness that the cell can be partially wet in the cell, but not wet along the edge. So if anybody are interested in knowing the detail, I'm more than happy to explain later. So next, let's look at the result. Uh, so we actually, for the first test case, we use the parabolic bow problem as a test case. This test case um, is look at the flow with this initial condition and the and we consider the the bottom to be frictionless. So and the analytical solution to this problem it just keep rotating perennially at the shoreline, uh, advance and recede, and because of it has no uh, a dissipation, any imperfection in the representing the wetting and drying front could actually propagate very far uh, into the domain. So in the numerical test, we use um, the domain of roughly 6 kilometers, and we use three different mesh resolution to because of analytical solution is available, so we use that to look at the convergence of the method, and we also look at uh, the figure on the right. Uh, that is the solution at the different location. So at the top one is the time series at the middle of the cell, while the one at the bottom is the time series at a at this point where the solution where is in the wetting and drying zone, and the different color in this plot uh, show different mesh result from different mesh solution. Blue being the cost at 20 kilometer, coral is a 10 kilometer, and red is exact solution. You can notice that that the solution in the middle is more or less distorted, right? And that progressively become better as we refine the resolution as one could expect. So, but when we add subgrid, right, this is solution from subgrid. We can see that the solution is more or less uh, in become insensitive to the mesh resolution, and in the wetting and drying zone, our not perfect. It agree pretty well with the analytical solution. So this plot on the right is the log plot of the error versus the grid size. Right? Blue is the result from standard MPAS, and red that's it from subgrid calculation. and the gray line that's it aligned with the first order convergence. So we can see that for the same can see that for the same resolution, subgrid is more accurate, and both methods roughly converge at the first order with the a standard convert a little bit faster, which it makes sense because of subgrid solution will converge to uh, standard solution when the resolution increase. And on the right panel, we plot the runtime and the error. So again, blue is standard and red is the subgrid. So for the same grid, you can see that the subgrid is a little bit more expensive than a standard. When we look at the cost per accuracy, let's say if one want the a solution with 0.06 ISME error, the standard method would cost roughly about 2.5 times greater than subgrid. So the next example, we consider the original limited domain area, but right now we use the real bathymetry. So we use the Buttermilk Bay problem that I showed earlier in the talk. So and we this system is contains several bays that connected to each other by a small channel that's particularly difficult to capture particularly to capture at high resolution is need to capture the channel. And the in the numerical experiment, we use a uniform mesh that tape the mesh over the area, and we use the mesh that range from 200 meter down to 64, and we use 3-meter resolution to represent the subgrid bathymetry, and we impose the tidal boundary elevation along this portion of the domain. So this movie shows the solution that we get from standard run. Move a panel on the left is when that from the cost grid, and from the a panel on the right most that's it from the high resolution. One can notice that there is no connection between the inlet and the bay periodically in the cost resolution. And I think now the movie is looping over itself. So let's go to the a subgrid solution again. The right one is when it simulate with the cost resolution, and the leftmost with the high resolution. So although not perfect with the low resolution, we can see that the solution are not that sensitive to the resolution. So so this plot we record the time series at different location in the bay. One is we put one station in the main bay and 2 stations in the upper reach of the bay, and one is near the inlet. So and it annotated by the black and red circle here. And again, blue is the color is represent solution from different resolution run. Blue is the solution when we use 250 meter, and green is the solution when we use 64 meter. You can see that the solution is quite sensitive to the resolution and and improve when we refine the mesh. So, and this plot, when we incorporate subgrid in the run, um, although not perfect, the solution become much less sensitive to the solution, as we see also in the parabolic bow problem. So this buttermilk bay and parabolic bow right now are in the E3SM repository. If you guys want to check it out, please feel free to check it out. So the next test case that we use is the inundation induced by Hurricane Sandy. This plot shows the track of Hurricane Sandy, which it made landfall as an extratropical storm near in New Jersey in October 2012. For the mesh, we use the existing MPAS mesh with 2.7 million cells and 8 million edge. And for this test, we only include the subgrid only in the area in red, right? So we can actually now add subgrid to anywhere in the domain. I mean, provide that we have a high resolution DEM. And for the bathymetry in this subgrid region, we use CRM, which has a resolution of approximately 30 meters. And the next picture shows the CRM topography being overlaid by the MPAS grid. Right? And in the run, we consider tide, and we use CFS for wind and pressure, and we use log law for the bottom draft, and we use 5 seconds for the time integration, and the run period is approximately 22 days. And both subgrid and standard run finish roughly use roughly around 5 hours to finish the run in with 700 core, and standard run being faster for 10 or 20 minutes. So this movie show the sea surface height over New York area during the Hurricane Sandy form subgrid run. Right, so yeah, one might see what you can see that the water level become really high in roughly October 29, 30. October 29, 30. For the validation, we use the water level at the observed water level at the gauge at no R gauge or at the no R gauge or at the USGS gauge, which is temporarily deployed during before the event and recover after the event. So the story is that in the open ocean location, the standard MPAS and subgrid version perform roughly the same, So I mean, this figure show the location of the station and the name of the station Noah being Noah Gate. So and a but for the coastal station, which is uh, station near near the small waterway or closer to the coast, Subgrid perform um, a yeah, better than the standard one. So for example, at this station at New Jersey, the Subgrid really well capture the the sea surface high signal. Oh, okay, I forget to mention that the blue is the offset and red is the MPAS, and the plot on the right is the standard uh, MPAS, and plot on the left it forms subgrid. So we are pretty happy with what we see from subgrid a result, and now we are working on including the more comprehensive forcing term that includes cell attraction and loading and internal type parameterization and with the ice cap. So with that said, the subgrid actually suffer from one issue that it's unable to capture this type of scenario of configuration where one have the barrier island. So for this um, situation, one would need uh, to degree of freedom to represent the sea surface high. But subgrid would work, but it would not give the accurate solution, and it can be arguably it can be mitigated by placing uh, the edge of the sail along the barrier island crest, and now is Steven is taking a step on that. With that, thank you for your attention and welcome any question or suggestion that you guys might have.